we have been discussing scaling down of MOSFET and also effects because of scaling down. We have jot down some of the parameters um, which are important as far as the MOSFET is concerned. One of the parameter was um, IDS, that is the drain source current. Okay, and we have seen yesterday that IDS scale will reduce by alpha times. Okay, if we follow constant field scaling, because we are reducing W and L, the dimensions, and also the voltages in the same proportion, right? Then we saw the channel capacitance. Okay, and channel capacitance also uh, so it will decrease by alpha times, with length will decrease by alpha times, whereas this Cox will increase by alpha times, because Cox, as I mentioned to you yesterday, it is basically epsilon over Tox, and this Tox will reduce by Tox by alpha. So this Cox will go to, so this alpha will go top to the top, and then it is like alpha Cox, right? So you see here also the capacitance will reduce. We have also mentioned that the depletion width associated with source and drain, etc., that will also decrease. Okay, so WD scaled, that is the depletion width, that will also uh, decrease by alpha the same amount. Okay, uh, and so on and so forth. So we also have discussed quickly that in digital applications the gate delay is very important. Okay, and the delay associated, the gate delay we can write uh, this way, that is this will have C by alpha over I by alpha and VDD by alpha. Okay, so this will um, also will decrease. Okay, uh, or gate delay will improve. Okay, what about power? We mentioned that uh, power associated with digital gates, maybe if we talk about a kind of inverter. Okay, so sorry, inverter, uh, maybe it is, there is a uh, um, capacitor from the next stage, and then we can uh, power is so this is charging the capacitor and discharging the capacitor and so on. So the power associated with digital gates, we can write FC VDD squared. Okay, if we just assume that the frequency or operating frequency remains the same, then P scaled uh, will be right. So you see this will uh, decrease by alpha cube if and the number of gates in the circuit may remain constant. If we just assume that, if we don't if we just consider the power, okay, associated with digital gates. Now power of an analog circuits, it is V multiplied by I. Okay, and if this will scaled uh, Here you see E by alpha square and so on. So then we uh, talked about transconductance, okay, and in case of transconductance, GM scaled, uh, you know that GM is mu Cox, so Cox will go alpha times, whereas W over L both will reduced by alpha, and VGS minus VTH, right? That will again decrease by alpha. So you see GM will remain the same, okay, and also you can calculate uh, resistance, output resistance associated with any fed device. So that's basically your uh, R naught, that is uh, 1 by lambda IDS, right? So if we find out R naught scaled, okay, that is uh, this will increase, lambda will increase alpha times, whereas IDS will decrease by alpha times. So your R naught will remain the same. Okay, why it is it will increase? Because lambda is nothing but delta L. You remember delta L by L over VDS, right? So this is VDS by alpha. VDS will go, sorry, over VDS. So this VDS by alpha, so that alpha uh, will uh, will multiplied with lambda, right? In the scaled R naught. So you see GM R naught, you see GM R naught is remains constant. Okay, this product. Uh, and GMR naught is basically intrinsic gain of weight, right? Intrinsic gain. Anyway, so this part roughly we have discussed. Okay. Um, Now the reason uh, this scaling or scaling of the reason this CMOS technology, okay, CMOS technology becomes um, so popular. There are various reasons. One, I mean, if you tell me main reasons, one of the main reasons is we managed to scale it down over several decades, and the second reason is the static power from CMOS is zero, right? Static power. When we talk about, say, any CMOS circuits, for example, say inverter, say simplest one. So the static power is zero. It's all about dynamic power, right? So that's the two key features. Because of that, CMOS becomes becomes popular over the years. Okay. Now, so one is scalability, and the second one is static power. Now, then we started. I think we started talking some aspects of um, uh, short channel effect. So because of this scaling, there have been several different effects. Those effects are known as short channel effect. Okay, there are various reasons why short channel effects develop. Okay, and let me jot down some of the effects and some of the solutions. Okay, one of the effect we talked yesterday was threshold voltage roll off, or change in threshold voltage uh, with L. Okay, so if you uh, so threshold voltage roll off. Okay, so if you, as I said yesterday, if you reduce the device length, MOSFET length, then some of the uh, immobile ion will be imaged by source or drain, not by gate. Okay, so let me repeat it once more. So this is my source. Okay, say this is my drain, and so there, this is my depletion region. Okay, and this is gate. So ideally what happens is these immobile ions under the channel, okay, will be imaged by the will be imaged by the gate charge, right? Will be imaged by the gate charge. Now uh, in short channel MOSFET, what happens is some of these uh, some of these ions uh, will be imaged by the source, okay, or by the drain. So source and drain has immobile ions, okay, they have immobile ions here, and they have immobile ions here, right? So these immobile ions will image this part and maybe these ions, right? So I mean the same thing is true for long channel MOSFET also, but that is very very tiny. That proportion of imaging from the source and from the drain side, the immobile ions which are present underneath the channel is much less. I mean less means proportion wise it is much less. Maybe if there is 2000 immobile ions here, maybe 5-10 immobile ions which is imaging by the source and drain. Whereas when you are talking about short channels, tiny MOSFETs, this is of appreciable amount compared to what is present here under the gate. So in other words, gate now needs to reduce or needs to form image of lower number of immobile ions. Okay, so this, so in other words, gate needs to have we need to apply lower voltage, okay, to form the channel. So if we plot VTH over L, okay, uh, the threshold voltage remains fixed, but as we go lower and lower in the channel length, there will be roll off of threshold voltage. In other words, threshold voltage is going to decrease. Okay, so that's one short channel effect. There are several, in fact, right? So let me point out some others. Uh, what will happen if width decreases? Uh, do you know? If so, this is decrease of length of the MOSFET. If we decrease the width or narrow down the width, do anyone knows how the threshold voltage will behave? I mean, it will remain the same, whether it will decrease or whether it will increase and so on.
It will increase.
It will increase. Why? So who is answering?
It's Saurabh.
Sort of. So sort of why it is going to increase?
Because of narrow width.
Right, but then yeah, for narrow width it will increase. You're right. Uh, you're right. So let me explain it a little bit. Okay. So the second I would like to mention is narrow width effect. Okay, narrow width effect. If I how to explain that? If I look from the top, okay, say I have a MOSFET here. This is the active region and this is the gate. You see, this is my gate. This is how you usually represent. If some of you have drawn layout in Cadence or Synopsys, probably you have seen, you are habituated with this figure. So or maybe in the book also, this is like a top view of the MOSFET, where this part is the active region, okay, and this is my gate, right? And we always draw the cross-sectional view like this, right? Say n plus source, n plus drain, and then the gate oxide and gate metal or poly, whatever, right? But we can also if we draw from this side, if we look from this side, okay, uh, then it will be something like this. So this is my W, right? This is my W, and this is my L, right? So if I look from this side, okay, uh, it will look like this. So this is my W, okay. Now I have other MOSFETs also. This is, I mean, in wafer, you know, or in your chip, you will have millions of transistors, right? So there will be other transistors sitting adjacent to it and so on. So there will be another active, so this is another active region, say source, drain, this is my gate and so on, right? So you have to isolate what I say, the adjacent MOSFETs, and the way you isolate adjacent MOSFETs is by having field oxide. So there will be field oxide here, okay, field oxide here, so that you can isolate adjacent MOSFETs so that they shouldn't talk to each other, okay. So this is my W, okay, and if you look from this side, as I said, if you look from this side, there will be field oxide. So this is your gate oxide, right? This is your gate oxide, and this is your field oxide. I hope you understand this. So this is your field oxide. So what field oxide will do? Field oxide will basically isolate adjacent MOSFETs. So this may be another MOSFET. So what it will do, it will this field oxide will be very, very thick, and then so this MOSFET will not be able to talk to this MOSFET because another formation of another MOSFET here is difficult, because the threshold voltage you need for that will be very, very large, right? So that is why you need thicker field oxide. Now this polysilicon, which is sitting on top of your gate oxide, okay, uh, is polysilicon is sitting here, right? So if you see now this, whatever voltage you are applying here, okay, it needs to not only form immobile ions here, okay, uh, but also the electric field will fringe, right? So they need to form immobile ions here also, okay. uh, so that in effect will increase the threshold voltage. So if you plot VTH over W, uh, so it remains constant. After that, the W is going to increase, the VTH is going to increase. Now the way um, this was managed later on is not using field oxide between adjacent devices, but you can have like trench isolation kind of thing. So I don't want to go in that direction, but the way trench isolation works is uh, basically, I think these will be vividly extensively discussed in the some technology class. But let me just tell you, in case of trench isolation, if you have like this is my n plus, uh, okay, and then your field oxide, instead of field oxide like that, you will have trenches. Okay, trench here, trench here. Trench means you create a trench, okay, and then you fill up with oxide, right? So if it is, you see uh, this fringing effect will not be there because it is very thick, right? Here it is very thick. The field oxide, if you go here, it is very thick, but here it is, where it matters is very thin, right? So as the field oxide is thinner here, the lines of forces, electric lines of forces, they manage to fringe, and they manage to form immobile ions, and that requires extra threshold voltage. I hope, is it clear to you? Is that okay?
Sir,
Yeah.
sir, this fringing field is the charge that is forming due to the fringing field is
Right.
not just below the gate, sir. Then, sir,
No, that's
how would the
not just below the gate, but you are applying the voltage to create this, because you see your gate is overlapped. Your gate is not your this polysilicon. This is if you this is going beyond your active portion. Okay, just to cover things. So so you can't we can't stop gate until this. As your polysilicon go a bit more, so your entire part, the voltage will not be confined until this. So the voltage will go beyond this. So that is why these image charges are coming into picture. Okay, are you with me? But
yes, sir.
this effect will decrease if once you say this polysilicon will go up to this, say, okay, for the sake of drawing, I'm so if this polysilicon is up to this, the voltage here, this fringing field is very less, because here it is much thicker. So this problem is solved in case of trench isolation here, because here it is very thick. This I'm drawing this part, but if you look here also, okay, so if I draw by looking from let me, yeah. So if I draw from this side, okay, this particular image of trench isolation, so that will be exactly same. So this is my W, okay, uh, and I have my trenches like this. Okay, so this is my trenches, this is my W, and I have this polysilicon, right? This is the side view, or the view from this side I'm drawing. So here, even if the polysilicon is here, okay, it will have hardly an effect, because trenches are much thicker. But the field oxide, the way it forms, okay, it is difficult to make thicker from the edge. Okay, it will be thicker eventually, but from the edge it is like bird's beak, right? So it will not be thicker. So that is why this fringing effect will be there, right? Now, so that's the second effect I thought I just mentioned. What about other effects? Gate leakage current. Gate leakage current we have mentioned. I just don't want to go into discuss that again. Okay, gate leakage current is coming because we are reducing TOX, and one of the way we can improve the situation by using high K dielectric. This part we have discussed, so let's move on. So this part we have discussed already. Now fourth is hot electron effect. What is hot electron effect? Hot electron effect is as source or drain are very close in case of short channel MOSFET. So basically these electrons they are basically zipped through between source and drain. Okay, they are very close, and near this drain side, okay, near this drain side, they might uh, they might collide collide with immobile ions and form electron hole pairs. So they can create electron hole pairs. Okay, holes and electrons will be created. Electron hole pairs they might create. Also, some of the electrons might penetrate the gate oxide and reach gate. The reason they might be able to penetrate, because you remember in generalized scaling we don't reduce the supply voltage as aggressively as in case of constant field scaling, right? You remember we discussed like we can't reduce the threshold, the supply voltage that much, because that will affect with other things, that will affect the analog designer to design the circuit, because we can't reduce the threshold, the supply voltage that aggressively like alpha, right? Alpha times. So that is why the generalized field scaling came into picture. So so the electric field also from gate side is quite large, because we fail to reduce VGS that aggressively. So that might take the electrons which is in the channel to penetrate through the gate oxide. So this will create leakage current in the gate. So this is more or less known as hot electron effect, because this hot electron effect is the reason hot the name came, because these electrons are very highly energized. Okay, and they can create electron hole pair. They can go inside the gate oxide and reach gate and so on. So the one of the way to solve this issue is if we can particularly the first part. Okay, if we can create a lightly doped region near drain. Okay, so one of the solution is lightly doped drain. Okay, often known as LDD, lightly doped drain or lowly doped drain. So so we will have like in MOS, like source and drain are they basically symmetrical. So instead of forming this lightly doped region near drain, we also form it also on the source side as well. What is the purpose of this lightly doped drain? So some part of the voltage will be dropped here. So that's, so whatever voltage you are applying between VD source and drain, some part of the voltage will fall across this lightly doped region, because this part is little bit more resistive. Okay, and so if some voltage will drop here, so that will basically soften or reduce the electric field in the channel, so the electrons will not zip through and form electron hole pair. Okay, bombard and form electron hole pair. So that phenomena will reduce if we can create, or people creates lightly doped drain, right? What else? So another effect I would like to point out is mobility degradation. Okay, what is?
Sir,
Yes.
sir, how this spatial region will affect the vertical electric field, sir?
No, it will not affect the vertical electric field. It will basically affect the this electric field between source and drain. Okay, so that's, so this will basically affect this electron hole pair generation. It will reduce the electron hole pair generation that impact ionization. Okay, so in other words, it will reduce the energy of the electron. Okay, but the second part I mentioned, sometime you will see in the book, they doesn't put it in the hot electron effect itself. They just describe it as a gate leakage current. Okay, so this part it will take care, that you are right. So this mobility degradation, why this mobility degradation takes place is the reason I just mentioned you in the previous number 4. This mobility degradation occurs because, as I said, we can't reduce VGS as aggressively. Okay, and if we don't reduce voltage at the gate, the carriers will be very close to the gate silicon interface, because the electric field they feel from the gate side is quite a lot. Okay, so the electric field in the channel from the gate side will be quite a lot, right? So they will be confined within the very thin region at the gate silicon interface. Okay, and these electrons, because of the appreciable amount of electric field from the gate side, they will scatter more. They scatter, they experience a scattering more. Okay, now this mobility degradation uh, has uh, has this mobility degradation will have various effects. Let me discuss it a little bit further. So this mobility degradation, people have modeled this mobility degradation. So one of the popular model is mu effective. Okay, that's the effective mobility is mu naught, that is a long channel mobility. Okay, plus 1 plus theta VGS minus VTH. Okay, this is one of the uh, empirical model. Okay, of mobility. Now here this theta is kind of I mean, mu naught is the mobility denotes in the low field, when the field is low. Okay, at low field, this is the mobility. Okay, and what is theta? Theta is known as fitting parameter. So by the way, I am discussing all this from Rajavi's book, but this part, narrow width effect, NW, is not in Rajavi's book. Okay, not there in the Rajavi's book, but rest of the things, whatever I'm discussing, more or less they are in the Rajavi's book. So this mobility degradation, uh, so this theta is known as fitting parameter, and theta roughly it is equal to 10 to the power 7 over Tox. Okay, and of course this is unit of theta is volt inverse, you see, because this volt inverse and VGS minus VTH, that is volt, so that they will cancel out, and mu effective unit will be of that of mu naught. So this is roughly, theta is roughly of the order of 10 to the power 7 by Tox. Okay, so Tox usually of the order of few tens of angstrom in short channel MOSFET. Okay, so you see theta will be more than 1. Okay, for example, if Tox is around 100 angstrom, then theta will be equal to 1. Okay, 1 volt inverse, right? And in case of uh, short channel MOSFET, even it is lower than 100 angstrom, right? Now see, so that way you see that this if you keep on increasing your VGS minus VTH, that's basically voltage overdrive, your mu effective will decrease, right? Your mu effective will decrease. So, sorry, this has an effect in your IDS current voltage relationship of MOSFET, because you remember that we can. So if we write uh, if we write if we replace mu with mu naught over 1 plus theta VGS uh, minus VTH, then you see, so if we replace mu with this factor, okay, and then if we say that theta VGS minus VTH say much less than 1, okay, if we assume that, then uh, then we can basically simplify it. We can basically simplify it with neglecting higher order terms, okay. So you see that now, so in case of MOSFET, instead of so in case of MOSFET, you see it is a quadratic square. It follows square law, right? The IV characteristic. So if you apply a sine wave at the gate, you will get like even harmonics. Okay, but but due to this mobility degradation, now you start getting uh, also the odd harmonics. Okay, also you will get odd harmonics here, right? So that is one effect you can uh, uh, see in case of mobility degradation. And we talked about mobility degradation can be improved by strained silicon and all that. So that's another effect. What else? So let's what else did I miss anything? Okay, I did mention DIBL yesterday. Is it clear to you? DIBL is clear to you? DIBL is okay. Okay. So I will skip it. The last thing I would like to mention is subthreshold leakage, subthreshold leakage current, or subthreshold conduction. Okay. Uh, how many minutes we have? We have 15 minutes. Okay. So this subthreshold conduction or subthreshold leakage current is very important factor as far as the scaling down is concerned. Okay. Uh, let's mention one more, then one more effect which I forgot to say. So there might be punch through might occur. uh, in other words, so I will come back to subthreshold conduction or subthreshold current in a minute. Let me just as so this effect also you might see as source and drain are pretty close. It might happen that the depletion region because of source and depletion region because of drain, they might merge. So if they merge, then you will lose control from the gate side. Okay, or right. So this merging you can stop by increasing the substrate doping. Now you shouldn't increase the substrate doping as a of the whole substrate, because that has some other implications. So what you can do, you can uh, put some uh, higher doping near source or near drain, okay, sometime in this region, okay. So if you put this kind of halo P plus region, that will basically prevent the depletion region to reach from source to drain, okay. So you can form this like this, or maybe uh, maybe a patch of uh, sorry, so that this depletion region will not go will not merge, okay, between source and drain. um, okay, so let's talk about let's talk about the subthreshold leakage current or subthreshold conduction. uh, I'm pretty sure that you know about this, but as we are discussing short channel effect, let me cover this part also. Okay, um, so this subthreshold leakage current or subthreshold conduction uh, actually it has very important consequence or detrimental consequence as far as the scaling down is concerned. What is subthreshold conduction or subthreshold leakage current? We know that uh, Q in the channel is basically, Cox VGS minus VTH, right? That is the charge in the channel. Okay, charge in the channel. Now charge in the channel is Cox VGS minus VTH. Um, but the thing, what does it mean that when VGS equal to VTH, this Q equal to 0, so there is no charge in the channel. Okay, so if you plot IDS over VGS, we know that it is something like this, right? So this is your VTH. So below VTH, we usually say that current in the FET is 0, right? But truly speaking, that is to some extent correct for long channel MOSFET, but that is not true for short. Even in the long channel MOSFET also there will be current below VTH, but that current is very tiny, very tiny. Okay, so we don't care about that current. But when we have like short channel MOSFET, this current is very significant. So this is known as subthreshold current or subthreshold conduction. So below threshold voltage, the amount of current below threshold voltage is known as so we are interested in here. Why we are interested in here? Because you see, the popularity of CMOS, as I mentioned to you, is because of the zero static or near zero static power of the CMOS, right? That's the popularity. But as we move to this short channel or scaling down the FET, below VTH, we will have current, and that current will be appreciable amount. And what it means, the static power is no longer 0. Okay. Now, why there will be current? There will be current because you see, say for an N channel MOSFET, say I have a P type substrate, right? I have a p-type substrate. Now and what we do, we form channel, forming inversion in inversion and form channel here by applying gate voltage. Now if we don't apply gate voltage, or if we have gate voltage below VTH, okay, we should not say there is no electron, because electron is the minority carrier in the p-type substrate, right? So if it is like a say if it is like 10 to the power 15 doping concentration, say, okay, of this substrate, that means if silicon is 1.5 into 10 to the power 10, is the Ni is 1.5 into 10 to the power 10 at room temperature, right? So that means the what is your minority carrier concentration? Minority carrier concentration is of the order of 10 to the power 5, you see. So minority carrier is not zero, channel is not there, but the minority carrier is there. Now the thing is, this minority carrier can give rise to current uh, between source and drain, okay, but this current is not drift current, this current is diffusion current, okay. Why it is not drift current? Because the carrier concentration is very low, and also usually when it is off, usually you don't apply very large voltage, so the electric field here is not that much, okay. So I'm not say, so the drift component of current is almost negligible, okay. So there might be diffusion current. Why there will be diffusion current? uh, because there is minority carriers here, but the concentration of carriers should be different, so that you can get this diffusion component of the current, okay. And there are ways to find out the diffusion component of the current. I'm not sure whether we should discuss that, but I mean but if you are interested, you can see books and see how that current can be calculated, okay. So diffusion current, you know diffusion is basically Q. So that's basically diffusion current density, right? dN is the diffusivity, and dN over dx is the concentration gradient. Now the concentration gradient will be created because you see the source voltage here, it is grounded, and here it has some voltage. So the concentration at this side and concentration at this side will be different, okay. And so if you can find out dN over dx, you will be able to calculate Jn diffusion, okay. And there are ways to find out how to the concentration of the electron near source side and near drain side, okay, so that you can find out dn dx. I'm just giving you some hints. If you want, you can carry out you can calculate this current, okay. All I'm aiming at is try to talk about subthreshold slope, okay. So that's basically channel length, n near source side and n near drain side. And n near source, if you look at any semiconductor physics book, you can write exponential q phi s by kt. Phi s is the surface potential, okay, surface potential. And this is n source, okay, and n drain will be so in the drain side there is you have applied some voltage, right? So that is exponential q psi s kt, okay, multiplied by exponential minus q vds by kt. So that is in the drain side, and you can put these two over L, you can find out Jn diffusion, and ultimately the equation you will get is basically exponentially related, okay. So ultimately you will get this. So this is nothing but capital D small n, okay, np0. Let me, I'm just for the sake of time, I'm just zipping through this thing. If you want, you can check from any semiconductor physics, advanced semiconductor physics book. So this will be like Jn diffusion. Okay, now if you increase this VDS, this will be very low. Okay, because KT over Q is 26 millivolt, you see. So VDS of 100 millivolt, maybe that means e to the power -4. So this part will go. All it depends on exponential Q psi x by KT. And it is possible to show that this Vg and psi s are kind of proportional. Okay, so in other words, your IDS, that is at subthreshold, is basically related to VGS minus VTH. Okay, and it is possible to show that this subthreshold slope, which is usually how many minutes we have? We have few. So you have class after 1. Do you have class after 1? You have class after 1 o'clock?
No, sir.
Okay, so can
Lunch
I take
break.
5 minutes? Can I take 5 minutes more?
Yes, sir.
Okay. Okay. So this Jn diffusion, you can find out from Jn diffusion, you can find out the corresponding subthreshold current. Okay. From because the from the current density you can find out current. Okay. All I am aiming at that this part will be close to 0, and it will depend on exponential Q psi x over KT. In other words, the current will be exponentially related. Okay, it's not quadratic. It is not following square law. In the subthreshold region, it is following the it is related exponentially. Okay, and so you can, it is possible to show that the current IDS okay, log, I'm taking log scale because it is exponential, you see. So log 10 IDS, it is possible to show that, I'm just skipping couple of steps. So if you are interested, you can try to work it out, or if you want me to work it out, we will do it later on. Okay. So it is possible to show from this step, if you just find out the relation between psi s and VGS from your semiconductor physics book, you will end up with, we will end up with this, and take the log, you will end up with this. Okay, where there is KT over Q, log K dash is basically a constant. Okay, and there is M. What is M? M is basically a factor which is M is basically a factor which is 1 plus CD over Cox. So if you um, keep on breaking it down, you will see that CD and Cox, this factor is also coming when you are replacing psi s with VGS, okay, or VG. Okay, then this Cox and CD will come. CD is the depletion capacitance, Cox is the capacitance, gate oxide capacitance. Okay, and now, so if you differentiate between this log 10 IDS over dVg with respect to dVg, you will ultimately get a nice small expression, which is this. Okay, or so this is log 10, this is log e. Okay, log e10 or ln 10. So this s, that is the subthreshold slope, which is basically inverse of that, inverse of this expression dvg. Okay, this is kt over q m ln 10, and this is millivolt per decade. Okay, and this kt over q and ln 10, kt over q is 26 millivolt or 25.8, and ln 10 is 2.3, and this is m. So this is 61 plus cd cox. So this is subthreshold slope, which is s is 61 plus cd over cox. Now this is millivolt per decade. That means if I plot log IDS over VGS, okay, in the log scale, you see if this is my threshold voltage, then beyond threshold voltage the current will hardly increase, maybe because you see it will go to linear region to saturation region. In the log scale, that is like only change of few milliamps probably, right? But below this VTH, it will follow this slope, right? It will follow this slope. So if you decrease by millivolt, so the slope will be how much order of magnitude of current it is decreasing. Okay, so so S is basically, you see 60 is the bottleneck, so minimum you can get 60 millivolt per decade. Okay, some often we get 80-90 millivolt per decade. That means one order magnitude of current will decrease once you are decreasing the gate source voltage below VTH. Okay, below VTH, if you keep on decreasing the drain source voltage, the current will decrease. Okay, but current will not be zero. In fact, when VGS is equal to 0, there is a finite current, non-zero current. Okay, now the thing is, this slope, subthreshold slope, is a constant, is doesn't depends on node. So if you reduce the MOSFET size, the subthreshold slope will remain the same because it depends on CD and COX. Okay, it doesn't depends on gate length. So what we are doing when we are scaling down the MOSFET, we are reducing the threshold voltage. So if you reduce the threshold voltage, you see maybe in one process node the threshold voltage is 1 volt. In maybe another process node, okay, maybe it is 1 micrometer process. Now if you go to 250 nanometer process, maybe that your threshold voltage is somewhere here. Okay, but your subthreshold slope remains the same. So your current is something like this, okay, in the linear and in the saturation region, but your subthreshold slope remains the same. So now you see your leakage current increases. Okay, so what we want large ion I off. So in the when the threshold voltage is 1 volt, okay, so you have like a cushion of 1000 millivolt before it goes to VGS goes to 0. So when VGS is 0, I off whatever be the current, say here if it is 1 milliamp, I of here will be okay. If we say like 100 millivolt per decade is the S subthreshold slope. So if it is like 1 milliamp, okay, so after 1000 millivolt, you have like cushion of 1000 millivolt. You see it will be a 10 order magnitude of reduction of current. Okay, whereas if it is like 500, if the threshold voltage is 500 millivolt, okay, so you will have 5 order magnitude of reduction. if you keep on reducing the threshold voltage, the leakage current or the current at when VGS is equal to 0 keep on increasing. So what is the significance of this? The significance of this is that your static power is going to increase, because below threshold voltage the MOSFET is quote unquote off, but you have appreciable amount of current because you can't change the subthreshold slope. Okay, your subthreshold slope remains the same, your VTH going to decrease, and the decrease in VTH will give you much larger I off. Okay, so your ion over I off will degrade. Now just I need one more minute. What people do, people use multi level 2 or more level VTH in present CMOS process. Why you need two VTHs, three different threshold voltages? Say for example 2 threshold voltage. Why do we need 2 threshold voltage? Because say I have 1 volt supply voltage. Okay, I have 1 volt supply voltage from the process, 1 volt. Now what I can do, I can have 100 millivolt threshold voltage in one case for some MOSFET, and for some MOSFET I can say that okay, I will have 500 millivolt threshold voltage. Okay, so now if you have like 500 millivolt threshold voltage, your it will be here. Okay, but if it is like 100 millivolt threshold voltage, okay, it is here. So what 100 millivolt threshold voltage will help me? It will give me more current. So speed of the device will increase. Okay. So in the chip there may be 1 million transistor, but you want faster operation maybe from 500 transistor. So those 500 transistor you have the threshold voltage 100 millivolt, because you want them to operate very fast. Okay, but rest of the maybe out of 10 lakh 1 million is 10 lakh transistor, rest of the 9 lakh something, you don't need much higher speed from them, so you use them for higher threshold voltage. Okay, you fabricate with higher threshold voltage, so that will reduce the leakage current, you see. So nowadays we have multiple threshold voltage in the same CMOS process of MOSFETs, so that the important MOSFETs from where you need faster operation, you can go for low threshold voltage. Okay, and you sacrifice your large off current. But for the MOSFETs where you don't need very high speed operation, you sacrifice the current. Okay, because VGS minus VTH will be lower, but you will be able to save the leakage current. Okay, I off for those. So this is all I have to say. Any doubt in this subthreshold slope part? Any confusion? No confusion, everything clear? No doubt?
Sir, which book of Razaway is this from?
So this